So I'm going to give a talk in 3 parts. First is a bit philosophical, psychological introduction to the field to make you reflect. And in particular, language is my language learning in robots, and communication is my field of research. Then second part, experiments and videos of robots doing things using AI. We don't build robots in my lab. We use ready-made robots for communication and trust. There will be something on trust also in theory of mind. Then the final part will be something which I started to preach on at the moment. It's a post-LLM, anti-LLM or post-LLM world. We need to reflect on what's coming next. We cannot really just say LLM will solve everything. Okay, so let's start with the first part. And this is the context in terms of applications where it's important that people and robots can communicate. Communication doesn't only mean speech. Communication also means non-verbal behavior, so pointing, even gazing. Depending where I look, you can guess what I want to communicate. So it's a series of different strategies for communication and different applications. So most of what I do is to do with robots supporting older people, so performing domestic support tasks. This is an area of Industry 4.0, 5.0, human-robot working together. So we have some projects, for example, with BA Systems on this. This is a company I'm consultant for it on touch sensing, which is related to also what you do for your research. And I recently started to work on robots for children. But in all this context, including robots in space, or even robots in a nuclear site where we are not allowed to go, and in Manchester many colleagues work on nuclear decommissioning and robotics. In all these cases, the person is at the center of the task. They are there in space, in a nuclear site, in a hospital, in a factory, in the home, to help us. So robots are tools. AI and robotics are tools. We will discuss about this idea of tools later. They are autonomous in the sense that we give them autonomy for some set of tasks to act as tools. So we are always at the center. That's why we often call this approach human-centered AI in robotics. And you will see why human in particular. Okay, this is just an example. It doesn't really matter. An accelerated example. But I want to, let's see if this starts. Let's look at this video. It's a long video, so I'm going to jump in different points. It's a previous European project I worked on about 10 years ago. This is not the real result of the project. It was the vision that we had at the beginning of the project. This project was special because there were 3 robots working together with the person. One robot in the home, your own flat. We call it Doro, domestic robot. We gave it names. So you can understand speech, you can use a tablet. Actually, my team, I used to be in Plymouth, in Devon. My team developed the interface for this, graphical interface, and then also the non-verbal interaction and speech interaction. Then you order your shopping, and you send this shopping list or medicine list to another robot, Oro, or outdoor robot, Oro. This is Oro. Goes to the shops, to the pharmacy, some personalization of recognizing which shop, which food. And then this robot takes the food to the warden. It's like if you stay in the student halls, you have a warden at the entrance, which will collect the food for you, and then it will take it to Doro. This is Coro, condominium robot. So Doro, domestic in your home with manipulation. These don't require manipulation, really. Okay, so this is the context. Of course, beautiful video. What did we achieve? Not a lot, which is good. We keep promising. Elon Musk said that by 2035, which is only 9 years away, we will have more billions of humanoid robots doing all our jobs, which is, in my view, nonsensical. But because you are the future robot scientist, maybe you will do it. But just to make you reflect, we have a vision of doing something complex, and then we have to focus. In particular here, we talk to the users older people, doctors, social services, and we decided together 11 small tasks which the robot had to perform. So no real cooking, but they will be carrying food and so on. And the reason I like this is because, going back to my field of research, which is language learning in robotics, and in particular, you will see not much, it's all about meanings. So language is communicating meanings. We call this pragmatics. In linguistics, in psychology, pragmatics is the area of language learning that has to do with exchange of information between people. So it's about the meaning in the context. Semantics is the meaning of an isolated word. Okay? So tea means tea, the powder or the leaves, or the hot drink. The context of tea is why I need it, why I like it, when I need it, and so on. Pragmatics. Semantics, one meaning in a word, pragmatics meaning in the world. So nowadays we have these super strong systems like LLM, ChatGPT. So I went to ChatGPT. I like the example of, I'm Italian, but I left Italy 29 years ago almost. I said they sent me in exile in the UK because I don't like coffee. This is the tea country. And then I discovered, actually, the British have nothing to do with teas. They use very cheap, I don't know, so apologies for the British here. I'm supposedly British now. So this is not the country of tea. In Europe, we think this is the country of tea. No, the tea is in Asia. I was in Turkey a few days ago, and it was a continuous tea drink. Real tea, real leaves, not just these cheap things. Anyway, I like tea, so I'm in the right country, kind of. And I'm getting old, so maybe one day I will have this robot in my home supporting me in everyday tasks. And I would like to have some tea, so I asked my robot, can you make me a cup of tea? So that's the prompt I gave to ChatGPT a few months ago. This is what I get. I get a recipe. So I have a robot, I'm paying for a robot, or social services, I'm paying for a robot to help me in my homes to avoid having to send nurses, which are expensive, or carers. And I get nothing out of these robots. I get a recipe. But what's the whole point of a robot is to give me a cup of tea. The pragmatics of my request, can I have a cup of tea, make a cup of tea, is to have a cup of tea in my hands. Remember, tea means something, semantics. Pragmatics is it's an action, it's a change of the world. So this is clearly not a solution. I know we can discuss this later at the end of my lecture. We have this RT, robot transformers and many VLA, they can do this. We will discuss what level of representation they use, but clearly this is not a solution. Or hoping the very early Google RT robotic transformers, where you have a vision system that converts images into words. You pass it to the VLA, to a LLM, and then you get some kind of motor primitives. This cannot work. We can discuss this later why. So hoping that these become primitives for a robot to do this is not working, and I'll tell you why. Now, I wanted to Google, I Googled a few months ago for an image of tea making because I was preparing my lecture. I had my ChatGPT example, and by chance, this is why maybe it's the country of tea making, I don't know. The British Standard Institute has a set of standards for making the right cup of tea, the British right cup of tea. So this is what you get, which is already better than ChatGPT that gives me a recipe that I have to make it myself, and at least now I'm getting some examples, right? I have vision, multimodal, examples of what I have to see. Implicitly, maybe there will be some affordances. We wrote a paper, a review paper with Lorenzo, is the first author on affordances. The object tells you what to do by their shapes, right? So the affordance here is to grab the hanger. So there is also implicit motor information. And then there are words, which is good because remember, ChatGPT gives me recipes words. But what I'd like to highlight here is that 80% approximate number of these words are highlighted in yellow because these are words which do not have a meaning which you can easily associate to an image. For a robot, it's very easy, or for a VLM, visual language models, you give me a shape and I call it teapot. You give me some leaves, some powders, and I can give it a name, I can classify it. But most of the things that you see here, average, how do you represent an average? How do you represent the word which, works, out, at, around, to? How do I represent a number in a robot? So you see, even getting a recipe with lots of words cannot lead you to a straightforward conversion into images and into actions, motor primitives. Because works, it's an action, but what kind of action? How do I represent the action? It's the context and so on. So this is to make you reflect that language is a very complex system. And language is not only speech perception, it's not only semantics, but it's grammar, the structure, the rules for putting words together, but then the pragmatics, what I do with these messages. Why is this, am I using also this? Because my main area of research at the moment is on abstract words, words which don't have a clear mapping into the sensory motor experience, into images of actions. I'll show you some examples on this later. So let's go back to where we are at the moment. So we have very powerful systems that you can pre-train, or in the past we used to pre-program a dictionary, like a database, into a system, which is what a VLLM kind of does in a slightly different way. But how many of you have heard of ELIZA? Okay, you know what ELIZA? When was ELIZA? ELIZA is the first chatbot, which is ChatGPT, chatbot. You had to write text. 1966, I'm 1967, so 60-year-old now the system. There was a very first ChatGPT, very simplified. Actually, it was a psychotherapist. They implemented a ChatGPT, a chatbot, which was acting like a psychotherapist. So don't forget, everything is connected. So there is history on chatbots that goes there. Of course, much more simpler. So theoretically, we can use an LLM, which is chatbots, to solve some of the problems, or most of the problems, or very few of the problems. But let's assume I take a robot. For practical purposes, let's buy a Pepper, this commercial robot, humanoid robots. Have you seen the Pepper? It's a humanoid robot with wheels. Software Robotics, Japan, built it. In reality, it was a company in France, Aldebaran, which originally designed the robot. So this Pepper robot, or any robot, talks to ChatGPT. It's a bit like the RT1, RT2, RTX, the Google robot transformers. So you receive an input, an instruction, make me a cup of tea. Here's something even simpler. What's the meaning of push? I rely on my LLM, or in the old times, you can rely on a dictionary. This is the American English Dictionary. So this example that I took from a paper, De Broglie, actually comes from the American English Dictionary. So the meaning, if I ask the robot, what's the meaning of push? The robot talks to the dictionary or LLM and will give me a reply. Push is, in the definition that you get in an LLM or in a dictionary, specifically this dictionary, is defined as to press forcefully against to move. Very abstract definition, but that's what we get when we do write words, linguistics and dictionaries, which is fine. So I have a robot. Robots can push things easily. They are very good at that. And you get this kind of definition, which is a bit too abstract, but let's investigate what the robot really understands for this concept of push, press, force, fully, against, to, move. Each word must have a meaning. So what's the meaning? I asked the robot, what's the meaning of force, which you are using to define push? The robot asks LLM or the dictionary, you get a reply, force is energy or strength, which is good, it makes sense, right? We would agree this robot understands, because it's saying things which make sense to us. Now, let's ask the definition of energy. We ask the robot, and the robot asks this dictionary or LLM. And look where the problem starts to appear. So, energy defines force, but then force defines energy. And if you continue this very simple minimalist example, you see that we are lost in this self-referential A modal. A modal means just text. Now we will say token. A modal means token only symbol system. No modality, no vision, no action. And that's the merry-go-round. Stephen Harnad, I worked with him. He used to be a professor at Southampton. He's an expert on these aspects of symbol grounding. So you go back to where you are. This is what's happening, which is not good. A robot must concretely, we say grounding, must put the feet on the ground, which means it must refer to some visual experience, motor experience. But just be clear, for visual, I don't mean only visual, we should say sensory. Sensory is also internal states. If I'm hungry, there is some internal molecular mechanism that tells my brain, you need to eat or you need to drink, right? So it's internal. Grounding is not only external, visual perception, it's internal, including If I close my eyes, I know that my hands are open and closed because I have sensors, proprioceptive sensors, that tell my brain more or less the location of my muscles and limbs and so on. So this is to make you reflect. It's a complicated world, and if you're not convinced, let's stay within philosophy, and let's watch this video with the explanation of the Chinese room experiment.
In the 1980s, the philosopher John Searle was chewing on this problem, and he came up with a thought experiment that gets right at the heart of it. And he called this the Chinese room.
The experiment goes like this. I'm locked in a room. Outside, there's someone who only communicates in Chinese. She writes out some questions and then posts those to me in the room.
Now, I don't speak Chinese, but I do have these books, and they give me instructions on exactly what to do with these symbols. So I look in the book, and if I can find a match to the symbols, then the book tells me exactly how to respond. So I can look up this response.
I can call this an LLM with a prompt, right? The question is a prompt, and you get the answer, word prediction. So it's the same idea. That's why now I call it the LLM room experiment.
That matches. So now I can post this as the reply to the message I received.
When our Chinese speaker receives the message, it makes perfect sense to her.
您最喜欢哪一本书？哪里是中国的首都？你梦里梦到什么？
As far as she's concerned, we're having a conversation in her language.
Just by following a set of instructions, I can convince somebody on the outside that I speak Chinese. And if I have a large enough set of response books, I can have a conversation about anything. But here's the important part. I, the operator, do not understand Chinese.
So I, the operator, who provides written, meaningful answers, does not understand. We accept it doesn't understand. He also says, if I had a big enough set of matching responses and questions and tokens, I would be able to have a very natural conversation, which is what we get with LLMs, right? So just reflect on the fact that an LLM that purely gets a token, it doesn't matter if it's written Chinese characters or if it's spoken text. Now we have DeepSeek OCR. You can do object character recognition. It doesn't really matter the format. At the end, you have tokens, and you get tokens. Meaningless. For the operator, these are meaningless. For the lady who is a native speaker, who asks the question, who understands the question, and she gets the answer, she thinks they are having a conversation. And I'm sure all of us, me and you, we have said, oh, ChatGPT understands. Because you ask ChatGPT for things and you think, oh, it understands. Actually, it's a big debate. Often, I would say, especially after you see my last part of the talk, I'm convinced that I should be able to convince you that there is totally no understanding in LLM, and some people still say there is understanding, which is good. In science, we need to disagree. Okay, so this is one solution. And now, one demonstration that there is a problem if you are only focused on a world of tokens. Let's call them tokens nowadays. Now, if you're not convinced fully, and this is really the example, at the end I say when people are not convinced, think of this example. Now, I'm going to speak to you in a language that you don't know. You are going to reply to me correctly. I will demonstrate this to you in a moment. In the language that I know, you will understand, but I understand. And I would think, whoever gives me the right answer, that you would have been in this country. It's not Italian, okay? So Lorenzo doesn't understand most of it. There is some overlap with Italian, like with Spanish, but if you know any of the languages, really forget about the language. Let's pretend these are, for us non-Chinese speakers, these are Chinese characters or Egyptian characters. So the question I'm asking you, and I need some of you to reply, quanti anni avevi la picciotta? It's like the Chinese lady giving in writing characters, and I can help you to do the symbol matching, but let's see if any of you, with the definition of some of the words, dictionary, is remember push, energy, strength, is the same idea. And then, of course, this is the easy bit. You have a book, question, answers, question, answer. So let's match the question to one of the three in the book. So, quanti anni avevi? Quanto petit, no? Quanti anni? Yes. We found the second page of the book as the question. The other side of the page, like in the video, as the answer. So I'm adding a few variables to make you work a bit. What's X? Picciotta. Okay. So quanti anni avevi la picciotta? So let's start to build the answer. Actually, no, let me stop helping you. Can somebody give me half a reply, a full reply? Quanti anni avevi la picciotta? Excellent. Bravissima. So you answered. So I think you are a Sicilian speaker. I'm from Sicily, the south of Italy. This is Sicilian dialect. 50% overlap with Italian. A bit more maybe. But this word doesn't exist in the Italian dictionary at all. It exists in movies because if you watch The Godfather, Picciotto is the low-level mafia guy. We say Picciotto. But it really means, sorry, I cannot tell you what it means because that's the next slide. So let's not worry about the meanings. What matters here is that I'm an LLM, you are an LLM, I'm giving you a prompt, and you give me an answer. Do you understand what we are talking about? But not exactly. Not at all, because if you know a bit of Italian, maybe you know that anni or Spanish means something, but it doesn't really matter. You don't understand. I hope. No, but do you understand what you know what picciotta means? Excellent. Anni maybe, avi, and then seti, who knows. But what did you do? Let's go in your mind. What did you do? Matching, question. Matching X, la picciotta. Avi, anni. We need to substitute A. So what can we do? We go into the dictionary. That's why it's important. We look for anni. Anni. That's not enough. So what's the context? Picciotta. So picciotta, anni, high activation, something in the middle. Oh, it must be this. So very good. This is what your brain did. Here at Zanzina, anni, only one level of activation, and if you know neural networks, if you know context activation, this is weaker.
Can I have a guess into what it means?
No. Because if you have a guess, it means you are mapping this to a language that you know partially. This is the only way you can guess it.
Well, also from what you told us about The Godfather.
No, but again, you are now using semantics which I gave you. So if purely LLM, you are an LLM here. There is no meaning. We will get to the meaning in a moment. Okay, so I can ask you many questions. Quanto pititto avevi la haddina? Let's do this. Quanto pititto avevi la haddina? Quanto pititto avevi la haddina? La haddina avevi? Pititto, haddina, assai. Okay, that's how you do it. This is the only thing you need to worry. Context, which is what you do. In fact, in LLMs, I heard a short video, I don't know if it's true, let's assume it's not a deep fake. The former CEO of Google, Smith, he said that we will solve the problem of AGI by having bigger context windows in an LLM, which is nonsense. But of course, more context, more co-activation, things that are related. But do we agree that there is no meaning here? Forget The Godfather, right? Okay, so next time I shouldn't say this. So how do we give it meaning? So John Searle is the philosopher of the Chinese room experiment. And then we have another philosopher, Quine, is a philosopher of language. John Searle is a philosopher of AI, earlier, 1980s, but one of the founders of this field. Quine is a philosopher of language, and he says he wants to demonstrate that identify the meaning of a word is very, very hard. So, and he say, these are philosophers, so they don't do real experiments. They say, like in Chinese room, let's imagine we are in a room. Let's imagine there is a dictionary. Let's imagine, for Quine, we go to the Amazon, where we discover there is a new tribe, South America, which has never been in contact with the Western world. Western and Asian world, with other cultures. We discover them for the first time, they speak a language, and they say the word gavagai when they and us, because we go to the Amazon, are in front of this scene. I don't want to use any word on purpose. So can you please tell me, I need here many answers, because this is the whole point of Quine. All the answers you're going to give me are right. So what what's the meaning of gavagai in this village in the Amazon? If they say gavagai when they and us are in front of this scene. I need many answers.
It's a girl.
Girl.
Bunny, grass, kids, love.
Very good. Okay, very good. So this is the whole point. All these meanings are correct. This is what it says. But we still get meanings, okay? So if the same people, so we have girl, we have bunny, love, what else? Grass. None of them is right, because if they say gavagai, when we see a different scene, what are the possible meanings? No girl, no dogs, because there was a rabbit, animal, and so on. It could be love. I love bunnies and I love dogs. This is the whole point. We don't know. But we do know because we learned language, so we don't need to be in philosophy to understand this. When we were babies, we heard the word gavagai or bunny or love or girl for the first time. How did we know gavagai meant animal, pet? So why did you, most of you, all of you, say the first possible words, girl, bunny, and dog, an animal? Why? Because you and I have, because of our psychology, cognition system here, have it's called bias, developmental bias, that says it's called the shape bias. When we learn words as babies, one of the first stronger mechanisms is to extract the most salient shape. If you do computer vision, the most salient shape. There are many shapes. The most salient, here it's, for Lorenzo is girl, normally it's rabbits, but he focused on girl. So the most salient shape is rabbit or girl, and we attribute the name to this. That's why we do it. Of course, we do this for concrete words. So shape bias is a known mechanism in development. Now, let's use, of course, Quine doesn't discuss the shape bias because shape bias was discovered later, 1960s. He says, look, there is a problem here because it could be rabbit, but it could be eye, it could be ear, it could be love, something that we see that we don't see. Is it the whole shape concept or part of the object? We don't know, and then you reflect on this. Now, let's do the same for Sicilian because I want you to understand Sicilian dialect. Now you can confirm your hypothesis. So what's picciotta? Shape bias. Girl. But why shape bias? It could be eyes, right?
It's because it's the biggest shape.
Very, very good. The most salient shape is girl. So it is girl, actually. That's good. Picciotto is the... Yeah. So picciotta is, I can confirm I'm Sicilian, it's girl. So if you like pancakes and you've been in the US, you know what this is, but it's a complicated concept. Let's focus on shape bias. Easy. Oval, right? What's oval? Egg, right? One shape, no ambiguities, color, variations, 2 or 3 colors, size doesn't matter here. And there is no issue of part of whole, right? In this case, it's very easy. This is easy, chicken, assuming it's the shape bias, of course, easy. So these are examples of concrete words, but here the shape bias is a bit tricky because it could be seeds, food, right? Pumpkin seeds, street food in Sicily, but also in some parts of Asia they eat street food, pumpkin seeds, toasted pumpkin seeds. So, these are concrete words where the mapping between the image, the perception, and the meaning is straightforward. Few ambiguities. Now let's go into a complex domain. We remember abstract words. 80% of the words which I'm using that you are using are abstract words, like in the recipe for tea making. But when we were babies, 80% of words were concrete. So we go through a transition, which is, we go back later to developmental baby psychology of robots. But let's go now to language of humans, abstract words. So what are the possible meanings of picca? I need 2 or 3 answers. Many? 3? Excellent. Eggs, it could be eggs. 1 egg, you say ovo. Many eggs, it's an exception of the language. But thank you for the perfect prototypical answers, because I need 3. because now I show you another example of picca. Who said 3? So we are refining the meaning. This is called cross-situational learning in psychology. Like the rabbit and the dog, 3 and 2, you know that it's not about the precise number. Many, 2 seeds is not many, but 3 eggs for breakfast is too many, right? Once I had 3 eggs, and they told me, Angelo, so many eggs. So we don't know, but let's continue. Cross-situational learning. So what's picca? Few. Very good. Because you are doing contrast learning, right? Okay, so you are doing this. Final example. What's the meaning of mangiare in Sicilian? I like pizza, so it could be pizza. Mr. Bean. Teddy bear. Right? Thank you for these answers. You are prototypical students in a good sense. What's the meaning of mangiare? What's the meaning of mangiare in Sicilian?
Oh, yeah.
What does mangiare mean? Sorry, what does it mean?
Is it cartoon?
Yes, it could be cartoon, but it's not cartoon. It's the action, eating, right? You saw a static to eat. So you static the image, you didn't think about the action, you thought about the static examples, right? Then when you see a video, you start to think, oh, it's about the event. So it could be the cartoon, it could be happy, right? I'm happy, I'm enjoying it. It could be many things. The whole point of these examples are concrete, abstract, nouns, verbs. So my research is on understanding how robots can be taught these basic linguistic words, concrete, abstract, nouns, verbs, adjectives, colors, and so on, using AI and robotics. Long introduction to convince you this. So what the approach we use is, let's not reinvent the wheel. We are teaching a robot to speak, to understand. Why are we creating our own theoretical setup of a robot learning example if we have a robot learning a language learning experiment, which is us human species. Plus we have the benefits of cross-cultural variations and so on. So the approach says, let's not do pre-programming, let's do bio-inspired training. And let's start from some concepts which are well accepted in psychology and neuroscience. First, you are not born with a language. You know, the insects, the bees, they do the dance, which is a way to communicate where the food is, but their language is innate, pre-wired. Here we say, no, we learn. It takes 1.5 years of age, 18 months, for us, when we were babies, to know maybe 10, 20, 30 words. By the end of the second year, 24 months, we start to do something which is a sudden increase of words, number of words, called vocabulary spurt. It's a sudden growth of words. These are some seminal citations, Tomasello. Then you will see in the next videos, we don't learn to speak, to use a language, by going to a class and sitting. We learn language when we move around, we explore the world. So embodiment, sensory motor experience is important. The brain is very modular. What function do we have here? What's happening here? You can make a mistake, it's okay. Lorenzo hasn't taught you. We can blame Lorenzo. Visual cortex. Vision is happening here. What happens here? Audio processing. And somewhere here there are meanings, but it's complicated. What's here? Motor control, okay? Here is planning, reasoning, and so on. Inside you have thirsty, and so on. Okay, so the brain is modular. So somebody could say, why don't we copy the brain? So we take a computer vision scientist, a speech expert, an NLP expert, grammar, a motor control expert. We put them together and we build a robot. Not because studies have demonstrated that although the brain is modular, language is not here. Here is the acoustics of language. Here is the meaning of language. Here is the motor representation of language. So you need them to develop the systems together. You need, this is very important, multimodal representations of concepts. Including for abstract concepts, you need to go down This is something which we disagree in science. Psychologists disagree on this. We have people that are called embodied cognition scientists. They say even abstract concepts have a grounding, indirect grounding mechanism on perception. Others say, no, abstract grounding is all about syntactic, symbolic regulations. Actually, you have here Gabriella Vigliocco, psychologist. She's a world expert on abstract word learning, and her theory is that abstract words come from our experience of social interaction. So learning to be social makes us think about concepts which are not concrete, what's a father, mother, what's good and bad. So Gabriella Vigliocco, in psychology, UCL, she studies abstract words, and we have collaborated together. And then finally, language is really social in the sense that we use it to exchange information. Theory of mind is my representation of your mind. You will see an example later of what we mean. So long introduction, end of the first part, to convince you, although it's almost the finish of the end of the lecture, to convince you that we need to use this approach. We call this approach cognitive robotics. If it's robotics, I guess you are somewhere there, right? Computer scientists, AI, mechatronics people, linguistics, psychology, including studies on animals. There are people have been teaching chimpanzees some very basic languages. In particular, if you focus on developmental, modeling how children learn, or baby robots learn, we call this developmental robotics. This is the book that Lorenzo mentioned, and this is the recent one. It's edited, it's open access. The second one is free in the MIT Press website. Okay, now I need to run a bit. So let's go into the second part, which is, you are roboticists and AI people. Show me how you do this. The way we do this is we take the psychology theory of year one, phonetic, no meaning, only sound, speech. Year two, you start with categories. You know that a banana is a banana because to eat a banana, you have to remove the skin. Even if you don't call it banana, you know as a baby how to eat a banana. And you know that it's different from an apple. But 18 months, you start to learn and say banana, yellow, hungry, and then later, year 3, you start to make sentences. Yellow banana, like banana, want banana, and then, can you please give me a banana later? And then we take ready-made robots, apply normally machine learning based on neural networks, even before transformers were invented, and we collaborate with many of these psychologists. Let's look at a video from many years ago.
So this is the iCub robot. And today we're going to teach it the names of some objects. Here a truck and a ball. So let's see how we go. Ball.
Ball.
Truck.
Truck.
Find ball.
Find ball.
So you see, we built a childlike experiment. Actually, as you see in the next slide, we copied exactly a set of 4 experiments from psychology, adding more from robotics, to replicate the same data. So remember the point. Instead of reinventing the wheel, I want to do some work on imitation learning of, grasping. You could set up your own artificial world, but maybe you could take a psychology or neuroscience paper on grasping and take inspiration from that, which is what we do here. Very natural, human-like. What do you do when a child is distracted and you want the child to learn? You call the child, we wave the hands, you shake you make a noise. This is what we set up here. So we set up an environment where we control the robot motivation to pay attention for its camera, to pay attention to a specific shape. Remember the shape? Actually, here we have 2 biases, shape bias and color bias. You see at the same time the shape and the color, because some concepts are a combination of the shape and the bias. And we set up a series of studies where we took the psychology studies, robot studies, and we wanted them to reflect above chance, below chance in specific conditions. It doesn't matter for you what's the difference between the different experiments, is that they correspond. And the second most important aspect is that for our research, the first 3 sets of experiments, we roboticists and AI people simulated, replicated the child data. Later, we created more experiments with our robots to change the setup of the environment, and we predicted that in one case, interference task, there is below chance behavior, but if you set up an interference task with changing the posture of the robot in a specific way, you get above chance, which means you get good learning. So in this case, here we simulate human data. Here we predicted human data. Why? Because we built a model which is so much constrained on what we know it's human cognition that we can almost use it for predicting what happens to this. They are not, let me say this is not an exact model of language learning. A model, by definition, is a simplification of some conditions, variables that represent clear mechanism. For example, shape bias, speed of learning, if you want learning rate, and so on. This is for you, specifically what's behind this. So this is all the work before CNN. So we had Cohen self-organizing maps. They are beautiful, simple networks because you get an output layer, which is a two-dimensional map, where the distance between the units is the distance between concepts. So if I have a map for color and a map for shape, color, if yellow is here and red is there, orange, which is semantically halfway, will be metrically in the map halfway. So the distance between the position of the units in this output layer corresponds to the similarity of the concept. And to make concept more discrete, you have a winner take all. In these maps, one unit, the winner, normally says, oh, I can see yellow, I can see orange, I can see. And then you have what you see color, what you see shape. Also motor map, remember here this is vision. Here is motor map. If I move around, our body, our brain is represented the body by having a mouth, hand, and arm, a leg, sorry. Mouth, arm, this, so head is here for motor control and perception. Arm is here, leg is towards the top. So you can build a similar mechanism. And then when you learn words and meanings are the colors, words are there, you learn these connections, these parameters. Using, for those who are familiar, Hebbian associative learning, very simple learning rule, not supervision learning rule, unsupervised learning. Now another example, because the world is a bit more complicated, this is more recent work, than just passively looking. We don't learn by looking passively, we learn by, as a child, touching object, moving object close to your eyes. Child's view, parent's view. I want you to watch this video more than once. This is what the child sees. This is what the parent sees. The parent is, in this setup, the parent is asked to, let me stop the video in a moment where perfect. So this is what the child sees. The parent is told, teach the child the name of some artificial objects. Let's call it microphone. Let's pretend the child at this age doesn't know the word microphone, okay? This is the parent world. This is the child world. If the parent says microphone, right, now, what's the shape bias telling the robot, the baby? That there is one object in front of your eyes. There are not three objects. As a parent, you would say, there are three objects. I want to teach the concept of microphone. Here is the microphone. You can point. No, you are a bit more active. You wait until the child plays with the object, and then you say the name. This is called scaffolding. Scaffolding is the mechanism of constraining the environment of learning. Scaffolding, like in the scaffolding of when you're building a new structure, so that you simplify the task, because now it's constrained. So here it's very simple. One shape bias, you can learn it. Or if I'm a parent, I can give the robot, the child or the robot, the object in front of its eyes to make it learn, which is what we did here. So this is the inspiration from psychology, Ewan Smith. We trained the robot.
This is a bottle.
Passive learning. Three objects, three shape bias. I need to know which one is most salient.
This is a cell phone.
Got it.
Now, scaffolding in learning.
This is a crop.
Remember, I am a baby. Sorry, in this case, this is the baby, this is the parent. The parent sees 3 objects, the baby sees 1 object. So CAP is very easy. So we show that this helps the robot to learn better. And then we do the test. Now remember, I said I work on abstract concepts, right? A prototypical example of abstract concept is numbers. How can I teach the robot the concept of 1 and 2? Because this is 1, right? I'm 1. We are 1 group. We live in 1 planet. So how am I going to visualize 1? So do you have any guess? How can we teach the robot about numbers? Let's go back to developmental robotics. How did you learn to count when you were babies? How do you do a sequence?
I guess you start with, say, 1, 2.
Okay, so you are using gestures, you are using your hands, right? This is what we do, right? In all cultures, different sequences of finger gestures. That's how we do learn language. Before we attribute these very abstract components of numerical cognition, mental mathematics, and so on, we start with the body. That's why I said within psychology and neuroscience, the people in the field where I'm also, the embodied cognition people say the body matters also for its abstract concepts. Other people will say no, and so on. So we did the same with our robots. 2 plus 2, a robot that can count his finger here, experiments in child psychology, it's the pointing that makes the difference. So here you count your fingers, different experiment, the robot is doing pointing. Child psychology, children, passive learning without gestures. You sit in front of a table as a child, you see objects and you hear their numbers, 1 and 2. Here, a puppet is pointing, or the child is asked to point, like in this case, and you see, you learn in the same session, you learn better. You can count, you reach a higher number of values that you can understand. So body is important also for abstract concepts. And then finally, remember, it's all about social aspects. So because we said pragmatics is about using meanings of words into the social context, I need to know what you want to do. I need to know your intention. And how do we read or understand people's intention? There are many mechanisms. One is, what does she want to do? Which object will she want to grasp? This is easy. The bigger one. Why is it the bigger one? Because we prepare the hand aperture when we are, before we perform the action. You would expect you go there and then you grasp it. No, we prepare the action. So body postures, movement, are cues to our internal states. So we do the same here. This is in collaboration with Honda Japan, our research unit, where we read with a Kinect, we read the skeleton of the robots. We apply some clustering algorithm from standard machine learning. So training phase, data collection, online data collection.
Show me the rules of the game. I will learn them so that we can play together.
So you get a camera, you get your Kinect, you extract the skeletons, right? This is what you are seeing.
What goal did you just show me?
And that's the label
Do you want to
for
show
our
me another goal?
body movements.
Yes.
Okay then, let's continue.
So training phase, show many examples. Here there are 4 examples, 4 goals or intentions for the human user, which implies 4 different motor strategies. We cluster them, we do a sequence, a Markovian sequence, we do some clustering, and now we can do the testing. The robot predicts your intention by observing your initial movements. So
We are building a tower.
prediction, I know what you're doing because I'm following you. And there are many examples of this. And finally, we go beyond simple observation of the motor behavior because we start to attribute mental states about things that you don't see. How do you know this is true? This capability is called theory of mind, TOM. It's very popular at the moment also in robotics, social robotics. So you show children at 3-4 years of age or later in development, this cartoon, one at a time. I'm explaining this, but the child should do this implicitly. So Sally, Anne, 2 location, 1 object. Sally hides the object here. She goes away. Then Anne moves the object. Then at the end, you ask the child, early in development or later, where will Sally look for her toy, the marble, the red marble? Young children say she will look there because they know the object is there. They don't think socially. They don't have theory of mind capabilities. All the children apply theory of mind reasoning. Sally doesn't know that the object was moved, so Sally will look for the object where she left it. So this is a mechanism. There are versions where you start to play with stickers left and right, which is what we did for our robot experiment. So first we do the training. It's a Vanderbilt is a version, psychology version with the stickers. Training, familiarization.
Hello, informer numbers here. Please look at me. Can you suggest me the location?
So you play the game a few times.
Left. Right.
Be aware, the label.
Hello, informer number 1.
Left.
The label is not for the robot, it's for us in the video. The robot has to implicitly understand this label.
Right.
So first we do the training, now we do the test, the prediction phase.
Hello again, informer 0.
Right.
I'm thinking I'd run to look based on your suggestion.
So you predict the person is trustworthy or not.
I was right not to trust you. I've never seen you before. I'll call you informer 2. Left. I didn't trust you, but I was wrong. Sorry.
And before I continue, when you saw the thing appearing on the right, that's a Bayesian network because we are creating these sequences of predictions and we train these weights, these probabilities. Now, this is called explainable AI. You can read the mind of the robot by explaining these predictions in these Bayesian networks.
Hello again, informer 1. I know the sticker is on the left. I also believe you would point left.
So you predicted the probability, and that's how you know what the person will say, according to the pre-training. Okay, I'm at the last part. I'm a bit running late. Do you want to have a break, or I have another 10 minutes to badmouth LLMs? Let's go to the LLMs. I think the debate will be on the LLMs. So I'm working on language, right, for the last 30 years. Suddenly, 4 years ago, LLM came. I could have been out of job, right? And actually, let me tell you this. How many of you are working with LLMs for your project? Very good, the majority, which is good. You are prototypical students. You know, what's the example of the typical student? It's you, most of you. Good, you are doing the right thing. I've criticized them, but I'm going to say they are important also. If you would have enrolled for your undergraduate MNG course, master course, 6 years ago, before GPT, LLM, half of you would have done LSTMs, half CNNs. Then 10 years before, you would have done non-neural networks. Okay? It's a fashion. It's a fashion in the good sense. Methodology changed, so you are doing the right thing because these are powerful. So let's reflect on the implication of having robots that learn language and then these LLM that do language. So positive. First, let me say something positive. Opportunities for LLM. First, I can't believe how well they work. You know, there are very few grammatical errors. Of course, they hallucinate, but actually hallucination, for me, I did neural networks 30 years ago when it was out of fashion. Hallucinations was the value of a neural network. The neural network must generalize. Hallucination means I create new knowledge. Of course, we are worried if I use an LLM to describe a fact, but the whole point of an LLM is that I learn many things and I can think by myself without intentionality. It's really, I can invent new concepts. This is my friend Tony Belpame, who is a social roboticist, an expert in social robotics. He thinks with LLMs we have solved social robotics. So I gave a talk in January. We were all both speaking, so I'm going to keep him. He's the enthusiast of LLMs. So even I'm impressed. I'm still impressed. Plus, let me say something. You watched the Chinese New Year dancing, right? So watch the video from last year, 25. The robots were the robots we know. Right. You can program a robot to do it. I saw some unit trees downstairs in the other building. So I'm sure you can all do this. What they did now, I can't believe it's true. I mean, let's not go into politics. It's the wrong moment here. There are wars. But it's impressive, isn't it, what they did from a motor control point of view. Maybe we are in the stage of LLM or of whatever they're using there, for motor control at least. But I can't believe it's working also for a standard LLM. Why are they useful? When shall we use them? As a tool. So you are doing social robotics. This is what Tony does. Then you don't need to script your necessarily all your dialogue. We used to have dialogue systems. An LLM can do this better for you. Or if you want to constrain, you don't want the LLM to start talking about forbidden topics. If you have a child, you can do some kind of RAG, right? You prepare your selection and then you give it to an LLM. It will create a nice sentence. For vision speech, if you want to recognize which object, speech is very good at speech processing. Autobiographical memory, because you can save events and then use them as a large context to find information. And for me, really, an LLM, it's like a new way to represent knowledge, collecting data. In the past, rule-based systems, you studied the knowledge of a domain, you prepare a set of rules, logical representations, predicates, and then you reason on them. The LLM does this for you with a data-driven approach, let's say, which is useful. In robotics, it's useful. Planning is all about robotics. And then if we go into VLAs, visual language action, not the RT, these robotic transformers, but the ones that are really trained in parallel, I think these are very good. There is multimodal. Are they doing grounding? This is what I study. If you apply your philosophical examples, does a VLA understand language? Because we say the LLM does not understand. Does a VLA understand? Maybe. It's something actually I'm working on at the moment. So positives, but negatives. LLMs, large language models, are not a language model for me because language is lexical, which is words, which is what it is, tokens, but it's phonetics, it's meanings, semantics, it's grammar, it's pragmatics. So maybe this should be called large token models, not large language. I'm not saying we should change the name, just make it reflect language goes beyond text and tokens. Plus, there is a problem with LLMs. If you train with an encoding of your words, which is an embedding that knows already the similarity between concepts, you are already cheating in the sense of giving information about similarity. Cat and dog, man and woman, will have similarities in the encoding, which already tells the system about the solution, let's say, of some of the meanings. But that's deeper discussion. So they are not language model in the real cognitive sense. There is no understanding, okay? Sicilian example, there is no a pure LLM. VLA, we said we can talk about this. LLM, there is no understanding, but we can, I know you like to ask questions, so hopefully you will get somebody will disagree with me on the understanding. No embodiment, there is no body, there is nothing. Again, we said that there is some information already in the embedding of the tokens, but let's not worry about this. So GPTs, the transformers, are the most non-cognitive neural network you can think of. What do I mean? They are, remember, attention is all you need, the title of the paper from the transformers. But attention for us, human being, animals, attention is selective attention. We can perform tasks because we can only pay attention to few concepts at a time. We have a memory capability, which is, we say, 5 plus or minus 2. We can remember in our working memory, short-term memory, between 3 and 7 concepts, typically, or actually chunks of concepts. So if you have 20 numbers and you treat them as pairs of numbers, you can remember, let's say, 7 pairs. But what do we have here? Transformer, an unlimited capability of reading at the same time. ChatGPT 3 used to have, I believe, 32 tokens. A token is not a word, but let's pretend it's a word. 32,000 tokens is like 50 pages of a standard book. So I'm an LLM, I have 50 pages in front of me, and at the same time, I see the first word, and I know that the first word with the second, with the third, with the position 31,999, I know all their similarities, co-occurrence, and so on. When we read, what do? We follow 2-3 words, and sometimes I can go back to the previous sentence if I'm not sure. So we do the opposite of what a transformer does. So it doesn't mean that we have to build human-like LLMs, but let's think about this. Of course, if you start to talk about human-like AGI, which I think is nonsense, it's recorded nonsense, which is fine. I can say AGI. The people that are promising AGI, they just want your billions for their investments. They will not deliver, likely for us, AGI in the short term, but we can discuss this later. So if you want AGI, a transformer will not give you AGI, for sure. A new version of new AI, many transformers, with other mechanism might give you AGI, but an AGI from a transformer, forget it. Attention is not all you need. On the contrary, selective attention is useful. There is no memory. Remember, if you are familiar with neural networks, we have feed-forward models, MLP, CNN, transformer, and then we have recurrent RNNs, LSTMs. So there is no real memory. Of course, the context and the chaining is used as a memory, but if you think of the one activation spreading from input to output in a transformer, it's a feed-forward system. So there is no real memory from this point of view. There is no working memory. And there is no time because you don't have a sequence. Normally, somebody said at the beginning, sequence learning, right? Numbers about sequence learning. But there is no sequence because we have encoding of the position, so there is some information there. But our representation of sequence is more about time, again, about selective attention and memory. And then, of course, let's not talk about the amount of data you need to train the system for. A 10-year-old child is better than an LLM. An LLM, ChatGPT 3, I read this in an article. You don't trust journalists too much, but there must be. I couldn't find a scientific paper. But they said that the equivalent of training a ChatGPT 3, the early GPTs, was to have 7 people reading all their life, no sleeping, no food eating, no playing. So these 7 people were born reading, lived for, let's say, 70 years, and then they died. 7 people times 70 years, it's 490. Let's do 500 years of reading. A 10-year-old child eats, plays, enjoys, cries, learns language. It's better in terms of data input than a 500-year-old person who has been reading all their life. So big data is good, but there are implications. And forget about the AGI, okay? But let's talk about AGI if you want. Now, I will conclude this by making you think how going back in science might help you to reflect on what is a solution. Of course, I do developmental robot, baby robot, so my proposal is let's start with baby-like examples. But there is a famous paper with a subtitle called The Importance of Starting Small. So now I give talks with this title, The Importance of Starting Small. Jeff Hellman, he invented simple recurrent network. In 1990, his paper had a very nice title, Finding Structure in Time. The paper is like Attention is All You Need. It was about simple recurrent network. We call them Hellman network. I spent a year in San Diego with him when I was a PhD student in 94, 95. So, and then he wrote 2 famous papers. 1990, Finding Structure in Time. He invented a simple recurrent network. And then 93, this paper on the importance of starting small. But let me tell you what he invented also. He invented, I don't really know if he was the very first person to do this, but it was 1990, the first paper. His task was to predict the next word. Okay, he created these data sets, and the task was next word prediction, which is what you do in training a transformer, right? A GPT is a next word prediction. system. So he already did this. In particular, he used in this 93 paper these sentences which are grammatically, in grammar they are called nested sentences. There's a sentence with another sentence. So cats chase dog, one sentence. Noun, verb, object. But boy who chase dogs see girls. Two nested sentences. Boys see girls, and then the boys who chase dogs. So two sentences listed. He took a simple Hermann network with an arbitrary number of units. He gave it this data. I think it was 500 examples of different levels of nestedness. And this network, with this specific arbitrary number, couldn't learn the task. The task was next word prediction. Of course, you need to understand, they are called long-term dependencies if you did LSTMs. The transformers are excellent at long-term dependencies because remember, I see word 1, 2, 3, 4, 5, 31,000, now 3 million words, I see them at the same time in terms of attention. So if you train on all these 500 examples, no success. And then he did two things which are important. One is called curriculum learning, incremental data. Why don't we give the robot simple examples first? Boy chases girl. Cat chases dog. And then after a while you give a nested sentence. Boys who chase dogs, like apples. So you do incremental learning, and it works. He says, but this is not what we do. Although we talk to children, it's called motherese, in a simplified way, linguistically, we really speak to children fully openly. So we don't really do very, very simple minimalist language learning, which is what they do here. So he said, this is not good. He said something else. Why don't we go into the brain of these systems, these babies, and we allow the memory capability, or the attention, in this case short-term memory, to grow over time, because older people remember better. Older in development, now I remember less. So, and it showed that basically if you know, as the way an Hermann network remembers the sequence is by copying the previous state. If I have 10 steps in my sentence, 10 words, I have 10 memory steps, or 9, because at the beginning you start. So what he did, you only allow a baby network to remember 2 words. Boy, chase girls. It doesn't remember the 3 words. Then you grow, you mature, you remember 3 words. Boy chases girls. So if you do this, maturation of memory, you get good performance. Very simple example to make us think that the data makes a difference, the structure of the data. Your maturation makes a difference. But remember, we are people, human beings, that go through many maturation stages. In particular language, there is something called critical period. If you learn a second language after 10 years of age, it's an approximate number, you will never be as competent as a child who learns multiple languages before they are 10. 10 is an approximate number. Why? Some are physical maturation. My articulations, I cannot pronounce some of the English sounds. If I've been a baby, my daughters who were born here bilingual, they have no problem, right? But it was a different. So we go through many maturation stages. Why don't we, to get real AGI, why don't we consider the data, maturation? The brain goes through pruning. Teenagers are meant to be problematic because apparently there are mechanisms in the brain which are going through restructuring. So there is a lot in the body, in the brain that changes, and we should consider this in building intelligent robots. AGI, but it doesn't have to be AGI. It means whatever you will be building in your systems. And I wouldn't show my conclusion, because maybe I've been talking for too long, we can have a debate, right? I don't know if you need a break to... So I'll finish here by repeating 3 messages. One, it's important to look at philosophical, psychological, neuroscience evidence. We're building robots, which are most of the time inspired by not only people, also animals. There is an area of research, you probably have done it, which is biomimetic robots. The octopus robots with flexibility in the soft robotics and so on. So bio-inspired, including philosophy. then real examples which combine what you do. But let's also, you will not be doing transformers maybe in 5 years' time. And if you become a professor, if you become a head of Apple, the new generation of people will want to do something else, which is an LLM, which is an LLM, not a CNN, it will be something else. Maybe some of you will contribute to discovering these new mechanisms. Okay, thank you.